Welcome to the first video lecture on Lakshya, a virtual laboratory designed by Department of Electronics and Communication Engineering, VCET Puttur. So myself, Shiv Prasad, Assistant Professor, VCET Puttur. Today I'll be discussing how to make use of this web application to conduct a DSP experiment remotely. Let's start the session. So you have various tabs. Almost all are related to some of the lab experiments related to EC stream. In DSP experiments, you have seven experiments which you can conduct remotely. The first would be the convolution. So let's try to implement this or conduct this. So the moment I click on the convolution button, so the browser is gonna direct me to the region where convolution information is addressed. So here it will ask some information which we are supposed to provide. So the convolution of two sequences takes two input sequence, x of n and h of n literally. So here I'm supposed to provide the inputs. So I'll take x of n as 1, 2, 3. So here the sequence which you are going to enter has to be separated using a space bar or white space. So in the same way, I take my second sequence. This is x of n, and this is your h of n. So give the inputs for a user to use this app. We have provided a information about how to enter the data over here. So you can see the example which you can directly include it over here. So here if I provide this to as the sequence, and the moment I give submit, it's gonna execute this convolution uh, using this mathematical expression. So this mathematical expression is for computing linear convolution, and this mathematical expression is for computing circular convolution. So I'll change the input, and second sequence I'll give it as 1111, so that the same result what is expected, which has been listed out over here, could be obtained. And this is also gonna give you the result, like the values. So you can see here the result has been listed out. You get linear convolution result as well as circular convolution result. The graph would also be addressed here. So in case if you want to write a program isn't being explicitly addressed over here, but the figures mathematical expression which is essential for anybody to write a record, everything is over here. So you can make use of this web app as designed. So second experiment is correlation again. So the moment I click my correlation button, so it's gonna drop down to the section where correlation GUI is being framed. So here again, I'll just enter the data. So let me give the data which has been evaluated over here. So I'll give 1, 2, 3 first sequence, and second sequence I'll list it out as 3, 2, 1. So this is nothing but you are finding the cross correlation of two sequence. So this is the expression for calculating your output result for cross correlation output, and this will be the result which will be generated. So again, press a submit button, so you can figure out the result will be listed just beneath this GUI. Okay, so here you have the result, the x-axis, y-axis, what is expected result, as well as the time and amplitude scaling factor, everything it will produce with the help of, even with the title as shown here. Third experiment is finding the fast Fourier transform, FFT. So here we will take the sequence as 1, 2, 3, 4, because this is actually the experiment which has been implemented over here. You have expression, and also you have how to calculate DFT for each of the points, and 4-point DFT is calculated as shown below over here. So again, press submit button. So you can compute, this program is going to literally calculate the magnitude response as well as the phase response. So this is the result which you'll be getting here. Okay, output would be a complex number. So it's magnitude as well as complex. I mean the magnitude and the phase of the particular DFT sample is being addressed here rather than the DFT output. Okay, so this is the result, which includes real part as well as the complex part. Its magnitude and angle response, you have it over here. That's your experiment number 3. Then you have FIR filter. So to implement this, we can define the order over here. So it will ask few questions. So order, we will consider it to be a odd always. Cutoff frequency could be considered as pi by 4, which is 0.785 exactly equal to. The window function could be considered as Hamming or Hanning window, which is the dominant window function used literally for FR filters. Then again, you just hit the submit button. So you'll be getting the filter coefficients in this case. So there are nearly 21 filter coefficients which gets displayed over here. With the help, along with that, you get the impulse response of a FR filter, which has been designed with the help of a Hamming window function, and you have the filter frequency response. This is your low pass filter, which shows the frequencies which are being addressed over here varies from minus pi to pi. So uh, it shows even the negative frequencies in this case. So centered Fourier transform it is. So this is actually the expected graph for FIR filter. Finally, you have difference equation. So difference equation program would ask you to provide the numerator coefficient values and denominator coefficients value. So here numerator coefficient value for this example, it's been 1 and 2. Denominator coefficients are 1, -4 and 3. So let's try to enter the same thing which is being evaluated over here. So I'll just give numerator coefficient as 1 and 2. The denominator coefficient, I'll take it as 1, -4 and 3. And the input sequence which needs to be filtered, let me give it as 1, 2, 3, and 4. So this is how the implementation takes place, and final result will be this 1836 and 130. Submit again, you should be getting the same result. You'll get the same result over here. Graph difference equation for the given x of n, what is y of n. Okay, then you have sampling theorem. Sampling theorem would have the signal frequencies. Signal frequency, I'll just take it as it's anything you can take. Let's say it's 10 hertz, so that I can convince you that this is actually a signal with 10 hertz frequency. Then you have a sampling frequency which shall take it a bit larger. So let's say that this is 1000 now, and the resolution of the input signal needs to be addressed over here. So we will take it very small. Uh, Higher than sampling frequency, you can take it equal to sampling frequency, not at all a problem. So this means actually the interval time for an analog signal, which we will be addressing here. You can consider it as a sampling rate for an analog signal, because we need to generate an analog signal over here. But analog signal generating is very difficult, so we have to define quite a very small interval. That interval is this very small. So give submit, and you can see the graph. The moment you press submit button, you'll be getting the results, which are the signal frequency, the sampled version, and the reconstructed signal. All three graphs you'll be getting it. So this is your graph. So this is your original message signal, the discrete version of the signal, and you have a reconstructed signal. Suppose if the sampling frequency has been reduced, like 50 hertz if I define, or 50 hertz if I define, then it would be pretty easy for us to figure out what's happening over here. Since I have made the sampling frequency was equal to 1000 hertz over here, so you have nearly 1000 samples between 0 to 1. So it's pretty hard to digest what's happening over here, but there are 1000 samples which are not easily perceivable over here. This is your result. Okay, and the last experiment is IAR filter, which again would ask some questions like enter the sampling passband frequency. You can give this as an example. So we will try to enter this passband frequency as in hertz as 1500, or stopband frequency we will enter it as 3000, the passband attenuation as 3, the stopband attenuation as 10 dB. Then we use The sampling frequency as 8K. So this is actually the expected answer. We will be getting the value which will be addressed, which is addressed over here. Give submit again. Yeah. Here you have the result. Results, order and cutoff frequency. What exactly do you have? Numerator and denominator coefficient values. And finally, the magnitude response. Okay, okay, so that's what I have.